Yeah. So, solutions are available. Many solutions are available. So, discussing that is not the objective of this session. The objective of this session is actually to make you see the surprise factor. Again, the session objective is to highlight, how they make things unfamiliar. And also we'll look at, try to see what are all easy things. We'll quickly, do them. Okay, so getting to the top is, I suppose, easier. Triangle mirror image. So if you just, mirror images, if you just tell me the option, I'll mark it. Looks like this. Is C correct?
B, sir.
Okay, B, fine. So mirror image, again, familiar. First two questions are easy. Third question, this again, we have done this many times. So both coffee and tea, that amounts to 35 plus 40 minus 10. Okay, suppose this is 65. Okay, so not C, neither C nor T. Okay, neither C nor T. That actually is 100 minus 65. That is 35. Notice again, this is an easy one. This variable substitutions, again, things are somewhat very easy. All it says is x square plus y square by xy is this term. So we have 2 square by 2. Okay, 4 by 2. So I suppose x minus y whole square is 0. So x is y. Okay, again, that's an easy one. 4 persons seated in a row. This is somewhat moderate, but it's nothing out of this place. In fact, there was, notice, there was a very similar question. We don't have a lot of time. Quickly, P and R cannot sit adjacent to each other. Okay, if Q is here, let's say this is right side. Okay, R can be, R can only be here. Okay, and if Q is here, R can be here, or R can be here. Then we have 2 options here, 2 options here, 2 options here. Total will be 6. Okay. Either P marries Q or X marries Y. So neither should happen. Here, X marries Y doesn't happen. Then yeah, neither is correct. Here P marries Q doesn't happen. No, this obviously is wrong. Yeah, no, this is in fact, we had a question like this in the mock before this was given. Okay, before this exam, we had a mock like this. The trap is for M and N, you start with, let's say, 6 and 4. Okay, you start with 6 and 4. M applying folding operation 1. This applies folding operation 2. Folding operation 1. Notice, so the way it is phrased, 2 sheets, folding operation 1, folding operation 2, they have defined it. Then this is being applied to that, this is being applied to that. Okay, it takes them time to actually read it and process it. But the trap is this. Folding operation 1 is applied to three times, joining short edges. So this becomes 3 and 4. Okay, the trap here is students tend to do this 4 and 1.5. Okay, but it's joining short edges. So obviously this is not correct. What you are supposed to do is it becomes 3 and 2. Then if you join short edges, it becomes, oh, you're joining short edges. I suppose this is a short edge, this is a short edge. So it becomes 3 and 2. And this becomes, yeah, this is exactly the trap that we will fall for. Okay, we have a tendency to do the same operation. So this becomes 2 and 1.5. Okay, so now we know the perimeter here, but notice this is relatively a simpler case. We join the long edges. So 6 and 6 joins, still the long edge remains the same. Okay, first joining, second joining, this becomes this, third joining, this becomes 0.5. Okay, in fact, the trap that I was mentioning was what I was actually, you know, slightly getting confused with. So be careful about it. Okay, and also see the way things are framed. It takes us some time to actually process it. So if you do this, I suppose it's 13:7. This is simple geometry problem. All we have to do was, you know, even if you don't remember, so all are equal lengths. So triangle 180 degrees. So we have a quadrilateral 2 times 180 degrees. So we have a pentagon, okay, 3 times 180 degrees. Okay. So one of this angle is, you know, this angle, let's call it y. Y is 3 times 180. That's a total angle inside a pentagon, divided by 5. Okay, that is y. Then this unknown here, x, will be 180 minus y. Notice if this is y, this is also y. And then your theta is 180 minus 2x. Okay, I think you get it. This as 36. You know, once you know why, finding this is simple, but you just have to recognize you have to start there. Function lambda is defined by this thing. Lambda as a function is given. Then notice numerator is just a number. So I mean denominator is just a number. Lambda only shows up in the numerator. All these brackets are there to confuse you, obfuscate your understanding. Okay, we have lambda. This is -1. Minus of that is 1, and this is 1. Lambda of 1 by this is -1. Minus of that is 1. Yeah, I'll just take a step back and I'll answer that. So lambda of 1 by 1, when p equals 1 equals 1, we have 1 minus 1 whole square. So this is 0. Okay. And humans have the text ability. I suppose this is very, very, very straightforward. No species, not correct. Okay. Unrelated skills, of course, I don't think it matters. No, this again is not intended. C is correct. Okay. So no, there is only 7 that is hard here. 8, if you think about it for some time, you should get it. Not a very hard geometry problem. Okay. 8 is moderate, let's say, if not easy. So if you are not getting, you know, 13 at this stage, there is some serious issue here. Okay, this is moderate. You tend to get confused, but you know, certainly shouldn't have one at this point.
Sir, can you please go to the permutation question again?
This one?
Yes, sir.
Yeah. So this is my right direction. What's your question here?
So my question is that S should be seated to the right of Q, right? If that's the case, isn't S and Q going to be only in the middle section, because P and R cannot sit adjacent to each other?
Yeah. So what I mean by R, I mean yes. Okay. So this is an yes, this is an yes, and this is an yes. So yes is to the right of, this is my right direction. Yes is to the right of Q, and there is a gap between P and R.
Okay. I see what I'm. Okay. Thank you. Yeah.
I mean, yeah, I just did not read it. I knew one of them should be to the right. So I just thought it's R. Okay, it's yes. Okay. So P can be here or R can be here. 2 cases. P can be here or R can be here. P can be here or R can be here. 2 cases. So, you know,
Okay, sir.
This is moderate, but certainly not, you know, undoable.
No, I just made a silly mistake, so that's it.
Yeah, the only hard question here is the spatial aptitude question. I would say, okay, fine, fair. And you know, the trap is also standard. And this question, I already gave this in a mock, you know, before the exam for students who gave it last year. And there also I highlighted the trap. If you're getting less than 13, there is a big issue here. Okay, let's get to 53. Okay, how do we solve this quickly? Math question. So notice these two are not independent. This is the same vector, scale vector. Okay, this is of rank 1. V transpose V rank is at max 1, and this is not a really independent vector. You are not getting anything independent out of it. So rank of V transpose V is at max. With one vector you are only getting rank 1. So if you use that, M should have a rank of 1. Okay, this logic and all that, okay, fine. No, but I couldn't really understand the questions. If you do this, V transpose V. Okay, so 2 times of that plus 3 times W transpose of this. You should get some matrix that is 0, 0, 0 and some non-zero number here. You should look at it and say the rank is 1. So whichever you do, simple things. So why don't you just find the rank of this matrix, not a hard matrix. Okay, consider a sequence like this. In fact, yesterday we are trying to, one of the classes we are trying to derive this. What quick means would be to xn tends to infinity. First of all, for it to have a value, if this converges, it will have a value. So if it converges, xn will be 0.5 xn plus 1. Okay, or 0.5 xn is 1, or xn is 2. So if it converges, the thing has a, xn is xn minus 1, and xn is a nice value, so it does converge. Okay, it might look out of syllabus, but did anyone read the question? It says we have this thing aligned along the wire along this direction. By symmetry, we know things should be, electric field should be radially out. This is the direction of electric field. So this is your z direction. That's the direction of the wire. Okay, no, no loss, nothing. Just know things are symmetric about this line, right? Electric field should be coming out of it. So the direction is R. This is out of syllabus question, I mean, for biomedical, but I did it because this is some basic common sense we have done in high school. Okay, so what are they actually asking in this question? Input-output relation is this. Input-output relation of this is given. If you give a spike, okay, it says something called H, you get spike, 2 times spike, spike. If you give this as an input, what is it? So what are they actually asking here? Yeah, see, this is impulse response. Discrete impulse response is given. They are asking, yeah, if you put at 0, if you apply a Dirac, the output of that is actually known as impulse response. They also given H here to hint at you. So what is given here is your H of n. And then this is your X of n. Peak value of the output. Output is Y of n. So we want the peak of this. Y of n is just discrete convolution. The moment you say discrete convolution, or they are asking for find discrete convolution, maximum value in the discrete convolution. Okay. So 1 to 1, and then you have 1, 2. So 1, 2, 1, 2, 4, 2. Right? Discrete convolution the way we do. So Y of 1 sequence is this sum, which is 1. Second term is this sum, which is 4. Third term is this sum, that is 5. One more term we have 2, and then we don't have any other term. Where is the maximum value in this Y of n? We have 5. Okay. Again, take a look at this. This is essentially the gate surprise factor highlighted very, very well. Perhaps if they say find discrete convolution, you can easily do that. Even if they say find the maximum value in the discrete convolution, you could do that. Okay. Or if they here clearly say impulse response is shown here, can you find peak value of output? That might also be more direct. Okay. So again, this is the surprise factor. Surprise framing. It's a very well-known, easy question. It's a surprise framing. See, again, notice this thing. That there are a couple of ways to do this, but the moment you say, okay, if it converges, xn should be this thing. The moment you realize that the answer is very simple, right? This also, I would say, is a surprise framing of an easy question. Okay. Let's go further down. There are, first of all, power factor cos phi is P by VI. Okay. This is a 2% error, 1% error, 1% error. Yeah, I think signal is much better now. So I had a similar question in IN 2014, where they meant percentage error is actually, that statistical error. But if you do the statistical error, you are getting 1 square plus 1 square plus 2 square, that is square root of 6. In this case, I suppose 2.4. You don't have that in the option. Perhaps it's tempting to pick perhaps B, but it's just, they are certainly not asking for the nearest value. Okay. Statistical. In IN 2014, this is what they meant by percentage error. That is a statistical error. But obviously in this paper, that option is not there. If you try limiting or maximum or absolute error, +1, all the errors are maximum, +2. All are in percents, so this is 4%. Okay, so you get 4%. So the best way out of this is they certainly imply, at least here, percentage means limiting absolute or maximum. Okay, so let's remove. Again, I refer to some high school books in physics. JEE also they ask this question, but percentage they refer to limiting. But let's get back to this convention. Okay, this is slightly different from what is there in the notes. And then we have statistical or likely or even RMS error. We have 3 terms here. So just make a note of it. It's okay, bilateral Laplace transform. How do you do this? Okay, it's at the end of the day, Laplace transform of the this kind of a function. So which property of Laplace transform are you using? Are you thinking about that? Okay, you could do a frequency shift, but negative. Yeah, notice if you are taking the property route, there is some room for confusion. Yeah, another answer there is, it's -infinity to 0. Just Laplace transform definition, -infinity to infinity. So e power t u of minus t, e power minus st dt. This is Laplace transform, bilateral Laplace transform, -infinity, so it's bilateral. And notice, because it's u of minus t, that function is non-zero only for reversed t time, right? Then this thing becomes -infinity to 0 e power t into 1 minus s dt. And in this interval, this function will any exponential like this, that is e power at with a greater than 0, notice we'll have a small a finite area in this interval we are looking at. So the moment we write this, we can say as far as 1 minus s is greater than 0, we have, this integral is nice in this interval. Okay, or s is less than 1. So it's either this or this. And if you actually integrate it, e power t into 1 minus s by, integral of that is 1 minus s, limits is minus infinity to 0. If you put 0, you get 1. If you put minus infinity, you get 0. So this is 1 by 1 minus s. So it's always, in the s minus 1 form. So this is minus 1 by s minus 1. So C. Okay. So point is, simple exponential. Yeah, if you know the properties and all that very well, you could try taking that route. But with this minus, sometimes things are confusing. Simple exponential function, why don't you just do the integral? Okay, exponential thermistor. You know that. We have the moment we have a root 2 and all, it's non-periodic. Things are not, you can't write this. Yeah, that is not periodic. Okay, it's not going to repeat. It's not periodic. And then step response as a circuit. Again, some questions from stability signals and systems and all that. For it to have oscillatory behavior, first order systems, there is no oscillation, only like the one transience is there. So at least second order. Then, one pole pair that is underdamped. As far as you have an underdamped system, things will oscillate. So theory question, fine. Let me quickly tell you for a n-bit flash type ADC converter. Okay, so you need 2 power n minus 1 comparators. Okay, so I suppose this is correct. And always when you change the input voltage, the LSB is going to change, not the MSB. Okay, this we haven't really covered in class. Okay, if you do not get it, that is fine. This I'm going to skip it. Microprocessor we are not going to cover, and single phase transformer, magnetized, excited with this. Again, transformer notice, power circuits not there. Let's skip this question. Nyquist plot, let's say not there in syllabus. Let's skip this. This, interestingly, we have covered in class by now. This is what is known as a precision rectifier. Precision rectifier. For current to flow here, okay, for current to flow, this has to be at a positive voltage. So if this is 0.4, this is 0.4, current will flow, and that current cannot come from this wing. That current needs to come from this wing. So this diode has to be closed, and if the diode is closed, it says it has a fixed voltage drop of the voltage drop always, for a diode occurs like this, 0.6. So this is 0.4. There is a, from this direction to this direction, the rise of 0.6. So this should be 0.4 plus 0.6. Okay. So answer here should be 1. Just in case you don't know, this is the Darlington pair, and notice there is one more question. Notice this current mirror. You can afford to skip BJTs as far as this. These couple of circuits. Okay, later on I'll show that. Darlington pair again could be easily analyzed. Okay, we have emitter base. Okay, then emitter base. Okay, this emitter current is given. This is I E1. All you have to remember is one relationship. Okay, relation between base current and emitter current. Base current is very, 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 very small. So this is the base here. Okay, that base current IB1, base of the first transistor, that's going to be very, very small. So given emitter current, okay, you multiply that by, you divide it by a very, very large number. That is 1 plus beta. Notice beta is large, 4950. So 1 plus beta, it's a very large number. Small fraction of IE1, that is IB1. And this emitter is same as this base. So your emitter in the current 2 is actually IB1. So you also know that this should be beta 1 because there are 2 transistors. So there's the only relation you need to remember. You need to know what is base, emitter, and all that. And once you know emitter 2, again, the base current, that is obvious. Take IE2 by 1 plus beta 2. That's it. Notice at the end of the day, your IB2 that you're looking for should be 1 by 1 plus beta 2 into IE2. IE2 is IB1. IB1 is IE1 by 1 plus beta 1. IE1 is known, so just plug in these values, you should get an answer. Okay, and this is the only relation you have to remember. Or sometimes you could also get an approximate value by realizing, so beta for this pair is actually beta 1, beta 2. So this base current is going to be related to this emitter current, okay, approximately 1 plus beta. You could also use this and get an answer within the range. Second method, okay. Notice this Darlington pair, they ask it again and again. And it's very, very easy. LPF wattmeter is this. Wattmeter can have this thing. Okay, maximum. So there is a low power factor wattmeter as a full scale of 300 watts. Maximum power factor of this is so VI cos phi is is P. Maximum it can measure is P. We have V, we have I. Question is what is cos phi for the given values? Okay. So just plug in the values, you get cos phi, I suppose, is 300 by 300 into 5. So it's 0.2. If cos phi exceeds that, then we run into issues. We exceed this full scale value. Okay. Quantization error. I think we learned about resolution. So notice 10-bit term, roughly the full scale deflection, you divide it by 2 power n minus 1. This is known as resolution. Right? This quantization error, notice resolution is this much. So when something, something is here, you cannot differentiate something halfway in between. So the quantization error is resolution by 2. Resolution by 2. Okay. Again, this is straightforward. So full scale deflection is given 10.23. I suppose for a 2 power 10 minus 1 is 1024 minus 1. So you have resolution as 10.23 by 1023. So this is 10 power minus 2 volt or 10 millivolt. And QE should be 5 millivolts. Half of this. So strain gauge resistances, all of this we have clearly seen. Very, very straightforward question. Resistance, yeah, minor trap will change to what? So del R is, del R by R is G epsilon. That's a definition of gauge factor. Okay. So from this find del R, and they are not asking for a change to what value. So the answer is R plus del R. So this is a trap. If you enter del R, it's a mistake. Okay, this is a trap. So this kind of a setup, what you have here is this is the pressure that you are trying to measure. This is atmospheric pressure over here, and the liquid level has a height difference of something. Okay, this is PATM at this end. And what you're measuring is differential pressure. That is, let's say, call this pressure P. What you're measuring is P minus PATM is what you're measuring. That should be equal to rho GH. Okay, this is diff pressure. And just find, rho is given, G is given, H is given, find that. You should get an answer. This might look slightly confusing, but there is only one interesting detail that we haven't seen in class. So let's spend a few minutes on this. What is a 3.5 digit 200 millivolt full scale digital multimeter? So this is crucial for this problem. Anyone, what is this 3.5 digit?
So it means three. So does it mean that three spaces, as in thousands place, hundreds place, and ones place, and one decimal, and then one after the decimal?
No, unfortunately, no. That is not 3.5. So this is, when we say that every mark matters, okay, in the professional world, every bit matters. Okay, you're designing something as an engineer, everything matters. This terminology comes from, you have 3 full bits. Okay, 3 full bits can be indicated. This bit we have issues. The way that is indicated is using this kind of a display. By turning on and on. 1, you will turn on and on this. 2, you will turn this on. Okay, 3, you will turn this on. 4, you will turn this on. 5. So all the 1 to 9 digits can be represented using this. Okay, suppose 1, 2, 3, 4, 7. 7 LED lights like this, right? So there is a light here, light here, light here, light here, light here, light here. So just in case you want to bring down the cost, okay, what they do is, so this has all 7. So any number can be displayed, any number can be displayed, any number can be displayed. So we have 3 full bits. There is some cost cutting going on here so that you could only display a 1. Or if it is not displayed, it's 0. So this chunk are not there. They have been removed from the design. Okay, so this is a 3.5 digit multimeter. That means you can have a 1 or nothing there. That means the highest number you could do is 1999. That is the highest number you could. Yeah, okay, so here, so the idea is using this, this is resolution of the this device, okay, so 200 millivolts is the maximum range. Resolution in volts will be by 2000. Notice that is 0.1 millivolts. This is the resolution in volt. Res in volt. We want to find the res in pascal. So we need to use the sensitivity information. If we apply 10 volts, this becomes, 10 millivolt per kilopascal with a 10 volt source sensitivity of this. So this is essentially 1000 pascals will give a reading of 10 millivolts. When will you get a reading of 1 millivolts? Okay, this is simple. I suppose this is 0.1 into 1000 by 10. Okay, this is, or roughly, this is 2 orders lesser. You have 2 orders lesser. So 10 pascals will give 0.1 millivolts. Okay, so again, sensitivity question we have done. The only thing is in this terminology, this will again show, but in this question, I don't think that knowing what a 3.5 digit multimeter is important, but here it does make sense. And this 2000 we are essentially getting approximately is 1999. Yeah, Swarnendu, you got that. So this 2000 approximately 1999. So I mean, so to get the resolution in volts, I used like the maximum numbers we can see there. Okay, fine. Amplitude modulation not there in syllabus. Let's skip. Move along. Interferometer again, technically we did not do, not in our syllabus. Let's do. So notice I have been giving the same question again and again, right? There is a reason for that. This is a trap that everyone falls for. They ask it. So find f dash of x equals 0. This is a critical point. Solution can be, at this point. Here f dash of x, I quickly, so minus 2x plus 10, I suppose x is 5. Solution can be at 5 or 10 or the boundary. Okay, find f of 5, find f of 10. Wherever is the minimum value, that's the minimum value. I suppose you get a minimum at f of 10. Okay, not checking the boundary, it's a usual trap. Okay, see again. Okay, one more question, easy question. This essentially is z plus 3 whole square. So critical point is -3. This is 1. This is -1. Critical point is somewhere over here, -3 outside of it. So integral is 0. Determinant of this matrix. Again, we have seen this. So determinant of this matrix into determinant of this matrix. Determinant of this matrix is 4 minus 6. Okay, this chunk. Determinant of this matrix is 4 minus 6 again. So this is 4. Yeah, this is again surprise framing. All you have to say, can you, let me give you a GP series. Can you find the summation? Okay, where is the GP series here? Notice the powers are increasing by 1, starting with -1, power is -1, power is 0, power is 1, power is 2. Okay. So quickly, if you multiply and divide by z minus 1, you get 1 into, z minus 1 power 1 plus z minus 1 power square minus z minus 1 power cube and so on. I multiplied and divided by z minus 1, or take this term out. So this GP, easy to handle. Okay, the signs are alternating. That we know we are looking at a negative term. Okay, so this is 1 by z minus 1, this outside factor, into 1 by 1 minus r. R is minus, r is technically negative of this, so 1 minus z. Notice, because signs are alternating, r is 1 minus z. And we know this, the r should be less than 1, mod r should be less than 1. So mod 1 minus z or z minus 1 doesn't matter. So 1 minus z less than 1. You could also say that as z minus 1 less than 1. So yeah, all of them z minus 1 less than 1 doesn't matter. So this term is 1 by z minus 1 into z. And suppose B is correct, I presume. Okay, B. Single phase transformer, 98% core losses. Again, transformer we did not cover, so let's not worry about it. Slip spring induction motor. Again, induction motor and all that we really haven't done. So, and also it's the MSQ, I suppose. Let's not take a blind guess. This is RH criteria. Okay, we haven't done this yet, but again, this is very much expected, which is why I thought, okay, one of the classes will do RH criteria. We have allocated for that. Okay. So let's right now, let's say this is hard control system question. We can always expect a question like that. Okay, but if you know RH criteria, you can easily answer this. Let's get here. Okay, OpAmp we could do. So I had some conversation about this with some of you. Notice there is a positive feedback loop, but the saturation values are not given. And so presumably this is still in the working range. Okay, because unless the saturation values are not given for an ideal OpAmp, okay, how do you deal with a comparator? In fact, there are two ideas here. One is first we have negative feedback and positive feedback, right? So is the positive feedback dominant, right? In that case, our OpAmp rules will not work. But the negative feedback is such that, okay, things are matching amp, okay, you can still apply the OpAmp rules. And here, which rule will not apply? Let's be clear, this virtual shorting will not apply. Water voltage here that applies here will not work if you know this is dominant. But in this case, you know, if it is dominant, nothing is given to say what we should do about it. Okay, saturation values are not given, so I'm not going to presume this is dominant. I'm just going to presume, okay, somehow negative feedback is the dominant one, and then we can still apply all the rules of OpAmp. Okay, then if you do that, I think RL can be easily found. Perhaps you will have to do some equation solving, but you know, this is not very hard. Quickly, the two equations will be, this is V here, this will be V here. Okay, so we have V naught minus V by 10K equals V by 10K, first equation. And then we have second equation here, 1 minus V by 10K plus V naught minus V by 10K equals V by RL. Two equations, two unknowns. V is unknown, RL is unknown, just find it, okay? That's solving you will have to do. But this detail will, you know, again, one of the classes will try to differentiate this, compare, contrast this with gate BM question and proceed. Okay, hard Boolean expression question. Were anyone able to simplify this? So it's a combination of min and max terms. You cannot use K-map. You will have to do traditional Boolean simplification. Was anyone able to simplify this? I did. Yeah. Okay. This Boolean simplification is one option here. Try that. If it doesn't work, I'll send you the simplification. But the thing is, if there is a simpler way, tell that here. Okay, all of you will get the simplification later. And this is also not that straightforward. It's somewhat hard. Is there a shortcut to answer this?
If the SOP part is only simplified, it will come to a very short expression. After that, we can use Carnot map.
Oh, this will become very, very short, is it?
Yeah, it will be simplified a lot.
Okay, so why don't you send in that part? I'll also send the standard Boolean simplification. Okay.
Okay.
But let's not spend time on here. This problem is hard. Now, counter timer set in frequency mode operation. Counter timer mode, period mode. Might be a simple question, but let's say, okay, we haven't really done it. Let's skip it. Okay, this is a thermocouple question. Good question to learn from. What can they frame from thermocouple? Notice, okay, there is a reference voltage and there is the actual voltage that you're trying to measure. You're feeding it into something. Then can you find the output here? I think given two temperatures. So what you are feeding here is the difference between this voltage and this voltage. Notice this is given to positive terminal, this is given to negative terminal. So you're feeding the difference between these two voltages. You have to sort of understand that from this block diagram. What you're feeding difference here. The moment you understand that, then rest of the things are simple. So you take V theta x, okay, minus V theta ref. This is what you are feeding. This times gain should be V naught. So question is, what is V theta x minus V theta ref? Notice this constants and all will disappear. 13650 will disappear. Okay, so you have 50 times the corresponding temperature. Kelvin or Celsius doesn't matter because we are looking at a difference. 50 times 100 degrees Celsius, okay, minus 50 times reference is 1 degrees. You feed that into the gain, you get V naught. Gain is given, so just use this. And notice this is in microvolts because this is in microvolts, so you can get the voltage accordingly. Okay, so feeding difference into the amp. Of course, that's the reason why you are also using an instrumentation amplifier, so that there is a voltage due to this, there is a voltage due to that. You feed in the difference. Okay. The moment you recognize that, the problem is simple. This question. So there is wind is blowing one way, so sound travels. Sound goes at this speed. Okay. So how long does it take to hear it back? This time taken as distance by upstream speed plus time taken by downstream speed. Slightly modified version of that using laser pulses. So time taken is time taken in air plus time taken in water. Time taken in air will be distance by speed. Okay, distance is 2 times 2 meters back and forth. By speed is 3 into 10 power 8. Then time taken in water, distance is, let's say x is what we are trying to find out. So 2 times x minus 2 is the distance back and forth. X minus 2 distance back and forth. Then speed is in water is 1.3. They are hinting your velocity is speed is different in water. So sea water is sea air, or supposedly in vacuum, by 1.3. Refractive index is greater than 1, speed is usually greater than 1, your speed is lesser. Okay, so technically 3 by 1.3 into 10 power 8, that's the speed, and this is given to be 100 into 10 power minus 9. So you can solve for x. Simple speed distance problem at the end of the day. This we have actually done in class. Okay, mux can be used to do combinatorial circuits. So quickly, S1, S0. Okay, you have the input here 0, 0, then 0, 1, 0, 1, 1, 1. You get I0, I1, I2, I3. Okay, so now we can easily write things down. So this is 0, this is 0, that is y bar, x bar. We get I0, that is z bar plus w. Or we get, this is 1. So x bar y, we get a 0. The system disappears. That is, we get I1, that is 0. Or, we have S1 is 1, x, y bar, we get I2, that is ZW. Or we have x, y, both are on, we get ZW dash or ZW bar notation. So this can be slightly rewritten in terms of, introduce plus W bar, and then the matter of identifying this thing. So it has, I notice it has a M0. So it is one of the fours. Does it have a M15? It doesn't have a M15. So I'm going to go with this. Here I can actually, we can answer. M0 is here. Now if for clarity, let's hold on these two terms. X, y bar, ZW plus X, Y, ZW bar. And this can be written as X bar, Y bar, Z bar into W plus X bar, Y bar, Z bar into W bar. Right? That is X bar, Y bar, Z bar. And then we have this thing. X bar, Y bar, W, Z plus X bar, Y bar, W, Z bar. So this and this are repeating, so you can remove this. But the point is there is a M0 term here and there is no M15 term. So 0 is there, 15 is not there. We'll go by B. This we have, interestingly, we have done in class. This again is somewhat expected. Mux, using mux for combinatorial logic. If you know how to do it, fine. Okay, else don't worry a lot about it. Okay, again, this is doable if you know what a JK flip-flop does and what a T flip-flop does. Okay, this is actually easy. You need to know JK and T. But let's skip this for the time being. Now we are back to a math probability question. Again, the area question is area type of question. You should recognize it. Typically, two-dimensional variables or area type question. So let's get the scales correct. So 1, 2, 3, 4. Again, we have 2 here, 4 here, 4, 2, 3, 1. Okay, this is our x, this is our y. We have x varies from 2 to 3. Y is uniform in 1 to 4. Okay, what is the probability of x less than or equal to y? So probability of y equal to x or y equal to x line is here. Notice 4, 4 is over there. This is y equal to line, so this point has to be 2, 2, 2. This point has to be 3, 3. So y less than x is here. We are looking for this area. So this area of this trapezoid by this total area. Okay. You could do it in many ways. Let me just skip the answer. Let's call this A1. Let's call this A. Your probability is this equals A1 by A. Let's say, this area of this triangle and the square by this area of this rectangle. That's what you're essentially looking at. Okay, how do you do this? The moment you have some complicated expression like this, it's Cayley-Hamilton, matter of implementing it without mistakes. So 2 minus lambda into 3 minus lambda. So lambda square minus 5 lambda plus 6 equals 0. So you have a square minus 5a plus 6i equals 0. Then you have a power 4 minus 5a cube plus 6a square equals 0. So this whole term is 0. So you're looking at determinant of 2 times I. Here is a trap. This is 4 times determinant of I, that is 4. 2 power 2 into I. It's a 2 by 2 matrix. So this 4 is 2 power 2. This k times I, k power n into this thing. This is a trappist here. So use Cayley-Hamilton and a property of determinant. Okay, electricity conductive bar. Bar is moved. Okay, not there. Electromagnetism, not there. Let's skip it. Toroid of C or G was an inner diameter. Toroid, okay, tempting, but let's again skip this. Air core coil having a winding resistance of 10 ohm series with resistance in series with a capacitor, excited by a 10 volt sinusoidal voltage. Angular frequency is this. Value of the capacitor is varied. Okay, maximum voltage is 30 ohm was observed across it. Skin effect. What is the inductance? So you have a capacitance, the inductance, and a resistance in series. Okay, so they are asking for what is L. Somehow find this L. This capacitor is variable, I suppose. So one definition of the connecting link will be Q factor. I suppose Q factor is omega L by R. R is given. Omega is given. So if you know Q, you can find this. Okay. Now, how do you find Q? Q can be found from one more interesting, definition given here. Maximum voltage observed. Okay. VC max is essentially, this is a definition of Q factor. Take the input voltage 10. multiplied by this, V in, you multiply it by Q, you get the maximum voltage across a capacitor or an inductor. In this case, across a capacitor. So 30 is Q times 10. So Q is 3. Q is 3, you know that, then just find L. Okay, this detail I did not mention in class, but just note it down. Maximum voltage across a capacitor or inductor in the series is actually given by Q times in input voltage. Okay, household fan. So okay, Jagruti might be like wondering, okay, what is easy, what is hard. We'll do that towards the end. 2 minutes. We'll just brush through the paper and we'll skip that. Household fan is this. Draws a current of this when connected to, this is RMS, this is RMS. Reactive power in the fan. So consume 60 watts. It actually drawing power of 230 into 0.3125. Okay, so reactive power, this should be equal to this term. Okay, let's quickly, if we multiply that, 230 into 0.3125, 71.85, 875. Okay, that square minus 60 square, 875 square minus 60 square. That is our VAR, this reactive power, because this is a right triangle. Again, this is something that we have done. Okay, where denotes a convolution operator. This is a nice question. Notice now we have to use some property of Laplace transform and do this. How do you get 0.33? Let's see. How do we do this? It took me some time to actually do this. So we know, okay, they are asking for final value, the final value theorem, but only once we cross this hurdle, we can apply the final value theorem. And the thing that is slightly missing here is f of t, u of t minus a property. You could use that. Okay, there are many properties available here, but the simplest would be using f of t minus a convolved with g of t minus. So g has a delay, this has a delay. That will be equal to fg, take the original convolution with a delay of, with the combined delay. We mentioned this while looking at properties of convolution. So why use this? Because a simpler function to study here is y of t. This is hard, okay? So minus 3t u of t convolving with u of t. Okay, this is simple. Now notice y of s is easy to find. This is technically 1 by s plus 3 by 1 by s as a partial fraction. This is 1 by s minus 1 by s plus 3. This 3 will remain if you multiply, so divide by 1 by 3. So your y of t is actually 1 by 3, 1 minus, so this is u of t, this is e power minus 3t u of t. I'm taking that u of t outside. So this is, let's call it y1 of t to be slightly clear. finding convolution, simple product. I know the Laplace transform of this, Laplace transform of this product of a partial fraction is easy. So I did the convolution this way. Then why mention this? So this is essentially our f star of g function. So y of t, one of them has a delay that should show up in this function. Is y1 of t plus 3. That is 1 by 3, 1 minus e power minus 3 t plus 3 u of t plus 3. Now, you don't need final value theorem. T tending to infinity, this term is 0. Y of t, t tending to infinity. That is no, this term is 0. U is anyways non-zero. It starts at minus 3. So this is just 1 by 3. This is hard. But the moment you realize this property will make our life easy, then things are fine. Mega, were you referring to this or a slightly different property, f of t, u of t minus a? Okay, you did it in a different way. Now we could do this in a couple of different ways, but for me, I found this to be, the simplest. Okay, now boils down to this thing. So surprise framing. So what are they actually asking?
Convolution.
Yeah, they are asking for discrete convolution. In the discrete convolution, how many non-zero terms are there? So essentially they are asking how many, again, let me write it wherever things are fine. So how many non-zero terms in discrete convolution? Okay, now only thing is this is lengthy. So 0 0 0 0 1 1 1 1 8 terms, 12 terms, 16 terms, 20 24 terms are there. You have to convolve that with 3 rows. So but still it's doable. Okay, do you recognize this question? I have been saying you. So sinusoidal input, sinusoidal output. You can see that here, right? Because although they ask it almost each and every year, students don't answer it. Your input is A times sine omega t. Your output is going to be B times sine omega t plus phi, where B is A into the gain of the system, modulus of G, and then phi will be just angle of G. Okay, technically, if input has a phase plus phi I, okay, then this will be phi I plus phi. But input here doesn't have a phase. So that's all there is to it. So take so A is root 2. A is root 2. Amplitude of the output is they are asking for B. So B is root 2 into modulus of 1 by S plus 1. What do? You evaluate S as j omega on the particular frequency. Okay. So omega is 1. So you are looking for answer is root 2 into absolute value of j plus 1. This is root 2 again, so answer is 1. Okay, they ask this again and again, but somehow students miss it. If they don't ask for amplitude, they might ask for phase. Phase is just angle of that thing. Yeah, they are getting to, okay, they realize, okay, initial value theorem, final value theorem, all the students know. But can we somehow obfuscate it or make the problem harder? Yeah, this again is surprise framing, full of traps. So when they say transfer function g of s, they mean to say CLTF. Okay, that is, if you are thinking of a feedback system, okay, you have 1 over s here, or let's say you have input u here, okay, output y here. Okay, they mean to say 2 by s plus 1 is actually g by 1 plus g in this diagram. So g is different. So to highlight that, let's call this, g1, g1, g1. So you are working with this g1 when talking about errors, but this g1 is given. You can quickly solve for the g1, not a big deal. Okay, so notice 2 plus 2g1 equal to sg1 plus g1. So we need g1. G1 is 2 by s minus 1. And let me just quickly verify that. Two by s minus 1. Fine. And then here, there is one more thing. Okay. The error here is u minus y. One more trap is the first trap. Trap 1. Then trap 2. This is u minus y. That is u minus g r. Okay. And then you get your error to be input by 1 plus g. But this error is minus ERR. Notice this is u minus y. What is given here is y minus u. This is what we usually deal with. So, but what is given is negative of that. Okay. So this error is going to be minus essentially now at okay, this is minus u error. So this, let me just note on the answer here. This should be s times 1 over s. Okay, negative because it's minus e error. So minus of this. This is input. This is the s in the final value theorem. Then 1 plus 2 by s minus 1. And you have to evaluate this at evaluate everything at 0. S is 0. So this 2 will cancel. This will be minus 1. Suppose the answer is plus 1. Yeah. So if you fell for the second trap, you'll get a minus 1 here. Okay, circuit shown below uses an ideal OpAmp. See, again, notice final value theorem, steady state error. We know they ask it again and again. So that's why control systems, we made sure we did that part. even in instrumentation paper, but fine, even if it's like a biomedical paper, they it's likely to show up. Okay, this question, ideal OpAmp, what is the output? Okay, no positive feedback, nothing peculiar here. So this is 5 millivolt. Yeah, you have to again write two equations and sum that. Let's call this voltage V. We have V minus 50 milli by 10K equals 50 milli by 12K. This is the first equation. Current here is current here. Then second equation, we'll have V naught minus V by 10K equals V by 1K plus V minus 50 milli by 10K. That is, this current is this current plus this current. Now you have to, you don't know V. Yeah, two equations, two unknowns you have to find for V naught. Is there a simpler way of solving this? No, two equations, two unknowns you have to solve for them. Okay, this is a current mirror circuit. Again, this is, even if you don't know anything from BJT, this is something that they ask again and again. Again, if you know the trick, it's very easy to handle this. Okay, this I, so idea is, so this is connected to the bases here, 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 here. Okay, so this current is, this is given. Let's call this I in. It should be this current, that is this collector current, plus whatever current here is. This is notice sum of all base currents. There is a base here, there is a base here, there is a base here, base here, base here. So this is actually 5 times I base. Okay. And then, so your I in is IC plus 5 times I base. And so why are we worrying about this part? Notice this is collector current, this is base current. So if you know IB, you know the collector current. This is IC, IB is very, very less. So you typically divide it by a large number. In case of IE, you divide by 1 plus beta. In case of IC, you just divide by beta. Okay, so, and this IC here essentially is IO4. IO4. So if you know IB, we can find IC. And how about this IC? We can write it as beta times IB is IC plus 5 IB. Okay, so you can find IB from here. IB is just IN by 5 plus beta. And once you know IB, you can find IO4. Okay, IO4 is beta into IN by 5 plus beta. One second, let me just make sure there are no mistakes here. Yeah, this is fine. Okay, so it boils down to actually remembering two simple things. I base is a small fraction of IC. No, so beta notice 20, so small fraction of IC. And then notice there are 5 bases here: first base, second base, third base, fourth base, fifth base. So this configuration, your input current is IC plus 5 IB. That you have to write it from the figure. This is general. And then if you want IB from IC, this is 1 plus beta. So you have to remember only these two. Then, BJT problems you could always very, very easily do. And you might note one more relation here. Using these two, you could easily see, notice IE is a beta IB plus IB. So actually IE is IE is, notice beta IB, that is IC plus IB. That is the current here is current here plus current here. So bottom line, they ask this again and again, current mirror or the Darlington circuit. You don't need to know a lot about BJTs. If you know one or two simple formulae, you can easily answer that. 713. Okay. No, 3-phase systems not there in our syllabus. Okay. Skip this one. 3-digit rectifier meter will rate. Oh, what is the answer here? 2000 volt range, a symmetrical square wave of frequency 50 hertz, amplitude 100 volt is measured using the meter. The meter will read. Notice, so 3.5 digit, and the range, in fact, the range kind of matches its, the specification. But anyways, let's get to this. What's the answer here? If you feed in square wave of amplitude 100, and it's also it's a rectifier type. So the square wave is rectified and sent here. Anyone?
Sir, would it be 100 volts only?
No, it won't be 100 volts. 100 is a trap. Input is this. So the rectifier, it rectifies and reads it. So it reads this signal. So where this is 100. But what does it read? If signal is 100, what should it read? Notice this 100 is actually average of this rectified thing. Okay. You rectify this, 100 volt is average. This meter will read RMS. So average to RMS, to convert it, you multiply by 1.1111 so on. So you take 100, you multiply by 1.11, you get 111 something. So it reads 111 volts. Okay. So yeah, this is a trap. digital meter actually reads the RMS value of the rectified thing. So average of the thing is actually 100. So it reads 100 times 1.1. This conversion, all of that is given in measurements. What is that? Measurements class notes. Okay, yeah, this is it reads RMS here. Okay, reading average will be etc. Reading averages. Current transformer rating. Okay, transformer we haven't done it, so we can skip this. Anyone solve this problem? Anyone? How many of you solved this question? Kelvin double branch. No one solved this. I told you, though it looks complicated, things are balanced. The conditions are very, very simple. Okay. Okay. This says it actually the double bridge is balanced. So this by this is this by this holds good under balance. So unbalanced condition, no Kelvin double bridge, at least forget it for now. So idea is we are trying to find R4, right? R4 by R2 equals R3 by R1. This by this is this by this. So this is under balance. And how do we know it's balanced? It says balanced. Okay. And so, I mean, this is given, this is given, this is given. All you have to find is R4. And I also highlighted this detail while going through Kelvin double bridge. Although bridge looks complicated, balance condition is when things are balanced, conditions are very, very simple. So your R4 is, just find that. 90 into 1110 divided by 100, 99. Okay, this is notice now they are mixing and matching couple of ideas. So they are, there is a RTD. Okay, strain is there, then temperature coefficient of resistance. So they are giving alpha. So actual resistance is R plus alpha delta T, right? R is essentially R naught into 1 plus alpha delta T. Okay, so let's call it R naught plus del R. Okay, again it's del R if it increases, R naught plus del R, here R naught minus del R, and then here we have R naught minus del R, here we have R naught plus del R. Okay, bridge. What makes this interesting is if they give the source voltage, we all know that this is like a full bridge, quarter bridge, half bridge is a full bridge. Okay, four resistors are changing and they are staggered. So we know this V naught should be, G epsilon voltage of the source. If the half bridge, you have a factor of half, quarter bridge, you have a factor of 1/4. So full bridge, no factor. But interestingly, Vs is not given. Current is given. Okay. So, okay, that is fine. So perhaps you might think you have to write, try to find the current here. So serially the resistance are same. So 0.5, 0.5, you can try to do that. But if we start at this voltage, current flow this direction, current flow this direction. So there is a rise here and a drop here. If you add those two, you get to V naught. So your V output voltage is, notice this has to be 0.5 milli. This has to be 0.5 milli because serially the resistances are same. 2 or not, 2 or not. Okay. And so the rise here is 0.5 milli into R naught plus del R. And the drop here is minus R naught, minus del R, so plus del R. So this will get cancelled. You have R times, this is in milliamps, this is in ohms. So you get, 2 R naught. So you get 1 delta R in millivolt, because this is an ampere. Again, let me highlight that. This is in milliamps. There is a 2 del R. So you will get, 2 times 0.5 is 1. So you have del R in millivolts. Del R in millivolts, we know is del R. Use a definition of G factor. R times epsilon into G. Epsilon is given. Gauge factor, where is it? Gauge factor is given. Then you have to find R. Okay, R is not 100. That is at 0 degrees. You are working at 50 degrees. And this del R is change is due to strain, but R itself is, different because you are working at a different temperature. So technically speaking, so this is not R naught. Okay, this is R. Okay, R. So R naught is at 50, at 0 degrees, but that also we can easily find because alpha is given. So your R, you know epsilon and G. So your R notice is, take the 0 degree Celsius resistance R naught into 1 plus alpha T. Alpha is given 0.05. 0.005 into 100. This is your R naught. Oh, sorry, not into 100. The rise is 50 degrees. Into 50. So you have alpha here, and you have what is that? Delta T here. Okay, that's it. So we know all of this. We can find what is V naught. But gate, when they want to make a problem hard, they combine things. They combine some kind of KVL with RTD with a strain gauge with a bridge circuit. So this problem is very hard, but again, the moment you get used to these kinds of combinations, this is doable based on whatever we did. Okay, let's move on. Pulse code modulation. Okay, let's say not there. Finally, okay, the last question for the paper. Let's quickly discuss this and we'll go through the paper. Okay, how do we solve this? This again is, surprise framing. This is a very well known thing. How do you do this? But again, the moment I say this, things are easy. Any guesses? One is we can go and go to the origins of this numerical aperture acceptance angle derivation and use that. Try to derive the results here, but there is something simpler we can do here. So problem is, let me try to again check for TAR condition at liquid core interface. Yeah, fine. Yeah, you could you could do that, but you could actually do something simpler. Okay, the real problem here is there are two acceptance angles. Two acceptance angles. You know, you have to get an acceptance angle here, but there are two. The resolution is, so when things are serial, the smallest acceptance angle will determine the acceptance angle here. It's okay, how you enter, but as far as some acceptance angles for this is the smallest, that will determine the overall acceptance angle. So this is a problem. There are two acceptance angles. So things are serial. Notice this is a fiber optic medium that is in serially with this medium. So we should have TAR in this medium. We should have TAR in this medium. So whichever medium has the smallest acceptance angle, that will determine the overall acceptance angle. Right? So we need TIR in both cable. That is the first cable as well as, let's say, the second cable. Okay, so smallest, this implies smallest acceptance angle is a combined acceptance angle. Combined acceptance angle. Okay, so that means let's presume the core liquid interface as the smallest. That cable. You notice at the end of the day, this is a fiber optic cable. This has the least acceptance angle. Let's say if that turns out to be correct. Okay, so let's say theta A here shows up due to the core and liquid. We know theta A is 45 degrees, 1 centimeter here, 1 centimeter here. 45 degrees. Okay, so sine of theta A is square root of, I'm presuming this, we have to presume this, verify whether that's correct, n core square minus n liquid square. Okay, we know theta A. Can we quickly find out this implies n liquid? And this is simple, right? Sine 45 is 7.007, square of that. .499. So I get quickly do this calculation for me, please. We know L core we know this is 0.707. So let me write things down. So n, say liquid square should be equal to n core square. N core is given 1.5 square, 1.5 square minus 0.49. Just give me 1 second. Yeah, 1.5 square minus 0.49. That I get that from squaring sound point, this term. And this is 1.5 square minus 0.5 is 1.75. And that makes n liquid as 1.32. Okay. Notice, is our original assumption correct? Okay. Presume liquid part has smallest theta a, which is why you proceeded with this. And we could also see this. N liquid is 1.32. So, 1.5 square minus 1.3 numerical aperture for this is smaller than a core and cladding. This is actually in this case greater than n cladding. Okay, this is greater than n cladding. That means our this is fine. If you calculate acceptance angle for core cladding and the core liquid, you get liquid to be the smallest. Okay, this is n cladding. So this means theta acceptance for core should be greater than theta acceptance for core liquid, core clad, because sine inverse of this, one of the square root terms is smaller. Okay, so our presumption is fine and our answer is, our assumption holds good, so this is the answer. But again, notice the surprise framing. If you recognize this fact, when things are serially, there should be TIR here, there should be TIR here. And that means, whichever TIR is has the lowest acceptance angle, that determines the combined acceptance angle, the smallest acceptance angle. And from there, we just presumed, find the value, and it happened to be smaller. Okay, so that's the end of it. Let's quickly do a calculation here. See, this is how. So nice part is, one of the most useful exercises we have done so far is this. The actual gate paper is going to be easier. I can assure you that, because there are no biomedical bits here, which are somewhat familiar to us. Okay, so however they frame the gate paper, it's going to be easier. First thing, no questions about it. That is why with this is paper. And having said that, questions will always surprise you. Having said, it's not like, okay, it's going to be cakewalk. Questions will surprise you. Get used to it. Used to all the traps and, traps and framing this. Let's just spend 2 minutes counting the thing. Let's say GA 13 marks. Or, to be fair, let's calculate the easy marks. Let's even forget, many of you are doing very well. Let's forget that. Easy marks, let's say what is moderate here. Moderate also skip. Okay, moderate. 1 mark moderate. Jagrati and Swarnendra, can you do parallelly so that at least we can verify? 1 mark, that is moderate or hard. Then 2 mark plus 2. Fine, plus 2. Okay. Then let's say moderate, plus 1. If you are sitting in examination hall for 3 hours, this is doable. If not by this, you can actually calculate the sum. So, okay, so either of this plus 1. This is easy. Okay, again, this we have highlighted. Let's say this is moderate, plus 1. Notice easy, easy, moderate. So plus 1 here. Then, okay, plus 1. This is also moderate. Moderate, plus 1, plus 1. Nyquist, moderate or hard. This technically is easy, precision rectifier. Okay, we have done this in class. This is expected, no surprises, no traps. Once you know the basic relations, doable. Wattmeter, VA cos VSP, easy. Again, no way out of it. There is a minor trap here. They are asking for quantization error. We have, what we used to ask is resolution. So not really a trap. Directly gauge factor, easy. Okay, they're asking for differential pressure. That might be a minor thing, but okay, let's say that's we note that down. Okay, this is, let's say, moderate. So there is 1 mark here. Okay, 3.5 digit meter, we don't know what it is. Moderate. So plus 1 here, plus 1 here. AM, we don't know what it is. Michelson, we don't know what it is. Plus 1. Then this is easy. We have stressed this enough times. Easy, easy. Let's say, okay, understandable, moderate. And this is a BM26 is a 2 mark question. Okay, so this is plus 2 starting from here. Okay, we have, okay, transformer, we don't know, plus 2. Slip ring, we don't know, plus 2. RS criteria, we don't know right now, plus 2. Okay, 2 equations, 2 unknowns. You can solve it for a 2 mark question. So let's not mark this as moderate. There is one more question. I'll make that mark that. This is, let's say, moderate, plus 2. Counter timer, plus 2. Okay, surprise framing, let's say, plus 2. There is no ambiguity here. Okay, straightforward question. I don't like to count this in moderate hard group, but let's say plus 2. Clock, okay, flip flops, plus 2. So I'm not going to consider this. Easy, okay, very, very easy. Again, easy, Cayley Hamilton and determinant. So we have a plus 2 here, and a toroid, okay, plus 2. Some basic things. Okay, right now it's, let's say, moderate. Again, plus 2. This is easy. You can't make a power factor question easier. This is hard. 43 is hard, so plus 2. At the end of the day, this is convolution. That's what you have to regularize. So okay, let's do plus 2 there also. This is expected. This is straightforward. This is somewhat obfuscated. So plus 2 here, 46. Then, okay, we didn't add there. There are 2 equations, 2 unknowns. Say solving is hard here, 47, say plus 2. Current mirror expected, okay. It's not moderate. It's an easy question. Whether we covered BJT or not, this should be easy. Not there, plus 2. And yeah, there is a trap here. Let's do +2 there for 50th question. 51 question transformer, I don't know, +2. This is easy. Okay, I'm not going to count that. This is combination of many things. Let's do +2. +2 for PCM, pulse code modulation, and let's also do +2 here. I don't think most got this. So how many marks are like moderate or hard? Summations. We have 2 of you counting. Can hopefully Jagruti and Swarnendra were counting. Jagruti is here. Okay. So I think perhaps they're adding or something like that. I am concerned about students who scored around 20. Okay, we should have a conversation. Okay, so okay, see 57 one count. Thanks for that. We got one count. 57 marks is, let's say, moderate to hard. And I have been considerably lenient here. So 43 is easy. Why are we not getting? Okay, so for 57 core, apt is 7. Okay, let's also 57 is one count. Let's also consider here apt is 7. Fine. So 57 plus 7. So that makes it 63 or 64. Okay, fine. 64. Even then, we have like 100 minus 63 is 36, right? Easy marks on a hard instrumentation paper. So this is keeping aside the surprise factor. So I'm really concerned those who are scoring less than 20, we should have a conversation. Others, notice I'm kind of feeling okay because 40, 50 you're scoring and all that. It means you are able to deal with surprise to some extent, and biomedical paper is relatively certainly going to be easier. So I'm feeling very confident about all of you scored around 40, even 30 plus. I am fine. Less than 20, with the amount of effort we put in, there is something going wrong. Yes, I will release it as soon as possible. Okay, I'll try to do it tonight, else I'll do it as a perhaps tomorrow morning or something like that. We should have a conversation. There is some issue, we should resolve it. Okay, and okay, fine. So we'll have a conversation, resolve it. And this is one of the best papers to learn from. We did it at the right time. So make use of this. This video will be available. Okay, whether you showed up here or not, make use of it, because this is one of the most important things we have done so far. Okay, so let's take a break now. Here's many are waiting for me. So I'll meet you again tomorrow. Biomaterials, biomechanics. We'll do a review of the entire notes. Okay, we'll start at 9 and we'll go till likely whatever it is, 6, 7 or something like that, with breaks. You will get one more bioinstrumentation surprise paper. It's an option whether you want to take a collide with that surprise or not. Okay, so let's stop here. So have a good one. I'll get back with questions, comments, in the group. Sure. Yeah. Bye.